Okay, let's dive in. Large language models, I mean, they're just everywhere now, aren't they?
Absolutely. It feels like they're transforming everything.
And really at the heart of making them better, making them smarter, is this core challenge. How do we train them effectively? For ages, the main method has been, well, predicting the next token, right? The next word or piece of a word.
That's the bedrock, yes. Next token prediction, or NTP, it's how these models learn from massive amounts of text without needing explicit labels. Self-supervised learning at its core.
But what if predicting that next token wasn't just about, probabilities and patterns? What if it involved something a bit deeper, maybe like reasoning?
Hmm, that's an interesting thought. Moving beyond simple prediction.
Yeah, and that's really what we're digging into today. We're looking at a research paper that introduces a pretty different idea called reinforcement pre-training, or RPT.
Ah, RPT. Okay.
Yeah.
So the idea is to bring reinforcement learning into the pre-training stage itself.
Seems like it. So, our mission here is to unpack RPT. We want to get into what it is, how it changes that fundamental training step, and, importantly, what the paper's experiments actually show.
Sounds good. Understanding the mechanics and the evidence. So the source is the paper itself, laying out the theory and the results.
Right. So, maybe let's start with the basics, the foundation. Remind us quickly about standard next token prediction.
Okay, so standard NTP, like we said, is the usual pre-training method. The model looks at a chunk of text, say the cat sat on the suitor, and its job is to assign a high probability to the word mad, assuming that's what comes next in the training data. It's all about maximizing the likelihood of the true sequence.
Got it. Learning the statistical patterns of language. And then there's reinforcement learning, RL. Where does that usually fit in?
Well, typically RL comes much later, after the model's been pre-trained with NTP. It's used for fine-tuning. Think RLHF reinforcement learning from human feedback, making the model more helpful or harmless based on human preferences.
Or things like getting better at specific tasks where you can check the answer.
Right. That's often called RLVR reinforcement learning with verifiable rewards. If the task is, say, solving a math problem, you can objectively verify if the answer is correct and reward the model accordingly.
But the paper we're looking at points out some issues with using these RL methods right from the start for the massive pre-training phase, doesn't it?
It does. Scalability is a big one. RLHF needs a lot of human input ratings, comparisons, which is just very expensive and slow to gather at the scale of trillions of tokens you use for pre-training.
And the RLVR approach.
That often needs special data sets where the rewards are already figured out or easy to compute, which might not exist for general text or might be limited to specific domains. So again, hard to apply universally during pre-training.
Plus, there's this risk they mention, reward hacking.
Yeah, that's a concern, especially if the reward signal itself is learned or complex. The model might figure out how to get the reward without actually doing what you intended it to do, gaming the system, basically.
So we have this scalable NTP for learning language patterns and powerful RL for later fine-tuning, but they have their own limitations. Feels like there's a gap.
That's precisely the argument the paper makes.
Hmm.
And it proposes RPT, reinforcement pre-training, as the way to bridge that gap.
Okay, so RPT. How does it work? What's the core shift?
The really interesting part is how it reframes next token prediction. It's not just predicting anymore. The paper calls it next token reasoning.
Reasoning. How does that work for just predicting the next word?
So the model is actually encouraged through RL to generate an internal thought process or reasoning chain before it predicts the next token. It has to sort of justify or work out its prediction internally first.
And the reward. Where does that come from if you're not using human feedback or special data sets?
Ah, that's the clever bit. The reward comes directly from the pre-training data itself. It's a verifiable reward based purely on correctness. Did the model's final prediction, after its internal reasoning, match the actual next token in the text?
So the model reasons, makes a prediction, and gets a simple yes or no reward based on the ground truth from the corpus.
Pretty much.
Right.
They use a specific mechanism, a prefix matching reward. Basically, the model generates a potential next token, and if that generated sequence is an exact byte-for-byte prefix of the actual next token in the data, and it lines up correctly with token boundaries, it gets a reward of 1. If not, it gets 0.
Okay, that sounds straightforward and objective.
It is. And it means you can use any massive text corpus, just like with standard NTP, but turn it into an RL training ground without needing any extra annotations.
So what are the upsides the paper highlights for this RPT approach?
Well, first, that scalability and generality we just talked about. It uses the same unlabeled text data as NTP, which is huge. No expensive human labels needed.
And the reward hacking risk.
Minimized, they argue, because the reward is just that simple rule-based check.
Yeah.
Were you correct? There isn't a complex reward function for the model to exploit.
Does it supposedly lead to a deeper kind of learning?
That's the claim. By incentivizing this internal reasoning step, exploring why a token might come next, RPT is designed to push the model beyond just memorizing patterns. It encourages exploring hypotheses and validating them, leading potentially to better generalization and understanding.
And you mentioned something about compute, how it uses its processing power.
Right. The idea is that these internal reasoning steps allow the model to spend more computational effort, more thinking time, if you will, on each token prediction during training. It's like applying techniques normally used at inference time to make models think harder, but baking it into the pre-training for every single token.
More deliberation per token.
Kind of, yeah. And the paper suggests this contributes directly to better accuracy.
Okay, the concept makes sense. Turning prediction into rewarded reasoning. How did it actually perform in their experiments? What did the results show?
They ran several tests. First, looking at core language modeling, how well does it predict the next token? They compared an RPT model, a 14 billion parameter one, against a baseline model of the same size trained normally. The RPT-14b model consistently showed higher accuracy in predicting the next token. They even broke it down by difficulty, easy, medium, hard predictions. And RPT was better across the board, whether it was just predicting directly or using its reasoning mode.
Was there any comparison to larger models?
Yes, and this was quite striking. The paper reports that the RPT-14b model's average next token accuracy actually matched the performance of a much larger 32 billion parameter baseline model that was trained with standard NTP.
Wow, okay, so the 14B RQT model performed on par with a 32B standard model, just on predicting the next token.
According to their results, yes. It really suggests that how you train, maybe using this reasoning-focused RPT approach, could be a way to get more performance out of a given model size, not just by scaling up parameters.
That's significant. Does this RPT performance hold up as you train it for longer with more compute?
They looked at scaling, too. The results showed that RPT's accuracy improved reliably and predictably as they increased the training compute. They even noted it followed a power law relationship, which is often a good sign for scalability.
Okay, so it seems to scale well. What about using these RPT models as a starting point for other tasks? Like, does this pre-training help with later RL fine-tuning?
That was another positive finding. They found that models pre-trained with RPT were actually a better foundation for subsequent RL fine-tuning. When they took an RPT model and fine-tuned it further with RL on specific tasks, it reached a higher performance level compared to starting with a model that had just received continued standard NTP training for the same duration.
So it's not just better initially, it's potentially more adaptable or trainable later on too.
Seems that way based on these experiments.
What about just general capabilities, things the model wasn't specifically fine-tuned for, zero-shot performance?
They tested that too, using benchmarks like Super GPQA and MMLU Pro, which test broad knowledge and reasoning. Here again, the RPT-14b model, when used in its reasoning mode, consistently did better than the standard 14b baseline.
Better than the baseline makes sense, but how did it stack up against the larger 32B model here?
Interestingly, it also outperformed the larger 32B baseline model on these zero-shot tasks, when that 32B model was used in its standard prediction mode.
So better accuracy matching a bigger model, good scaling, better foundation for fine-tuning, and better zero-shot generalization on complex tasks. That's quite a strong showing.
It is. The results presented are definitely promising. The paper also tries to shed some light on why it might be working so well by looking at the actual reasoning process.
Right, looking inside the thought process it generates. What did they find there? What kind of reasoning patterns did the RPT models use?
They analyzed those internal chains of thought. Compared to a baseline model just told to solve the problem step by step, the RPT models apparently use patterns identified as hypothesis generation and deduction much more frequently.
Hypothesis generation and deduction, as opposed to what?
As opposed to a more straightforward breakdown strategy that the baseline tended to favor. It suggests RPT might be encouraging a more exploratory and inferential approach to figuring out the next token, not just following a simple script.
Can you give an example of what that RPT thinking looks like based on the paper?
Yeah, they included an example which is quite revealing. Instead of just spitting out the next word, the RPT model's internal trace might describe analyzing the sentence context, like figuring out it's about calculating vector magnitude. Then it might brainstorm options. Should the next word be examples, steps, methods, It considers structural things like nearby formatting. It even looks at tiny details like whether a space should come first.
So it's really like weighing options, considering different angles.
Exactly. The example paints a picture of a much more deliberative process. Analyze, brainstorm, check structure, check details, then predict. It feels less like pattern matching and more like constructing an answer based on evidence from the context. It aligns with those ideas of hypothesis and deduction.
That example definitely makes it clear it's not just predicting, it's constructing the prediction through a kind of internal argument or exploration.
Right. It supports their argument that RPT cultivates a different, perhaps more robust, way of processing information right from the pre-training stage.
Okay, so let's try and wrap this up. The core contribution here seems to be RPT reinforcement pre-training as a new paradigm. It takes next token prediction, the standard task, and turns it into a reasoning exercise rewarded by correctness using RL, all fueled by the existing massive text datasets.
That's a good summary. And the key findings reported in the paper are pretty compelling. Improved next token accuracy, potentially matching larger models, good scaling properties, providing a stronger base for later RL fine-tuning, and boosting zero-shot performance on general reasoning tasks.
It also seems to encourage different internal processing, more hypothesis testing and deduction compared to standard methods.
Correct. The evidence presented suggests it could be a really valuable technique for building more capable LLMs.
So here's a final thought for you, something to mull over, based purely on what we've discussed from the paper. It describes RPT encouraging these reasoning patterns, hypothesis, deduction, just to predict the next token. Does that maybe hint that reasoning isn't just some high-level skill we add on later, but perhaps it's more fundamental, maybe even necessary, simply to generate text coherently and correctly in the first place?
That's a provocative question. Is reasoning inherent in good language generation itself? This paper certainly seems to nudge us in that direction.